So earlier we've seen how to prepare alcohols from aldehydes and ketones by simple reduction of aldehyde and ketone using lithium aluminum hydride and sodium borohydride. And we could get the primary and the secondary alcohols. There's another way to prepare alcohols from aldehydes and ketones. And these reactions, we call them Grignard reactions or alkyl lithium reactions. The Grignard and the alkyl lithium have this structure over here. So this is the Grignard and this is the alkyl lithium. Both, they have an R negative charge in there. This is called a carbanion. It's a carbon with a negative charge. These two reagents, we call them organometallic reagents. It's organo because the negative part is an organic carbon. And it's metallic because it does have a metal. So magnesium is a metal and lithium is a metal. We will study how to prep those in organic too. But for now, we're just going to look at the reactions with carbonyls, with aldehydes and ketones to make different types of alcohols. Now, every time we look at a negative charge, negative charges can act as bases and they can act as nucleophiles, especially if they are negative charges here. Here you have carbonyls. So these two, they act as nucleophiles and they act as bases as well. But the rule says that they're always going to act as a base every time there is an acidic hydrogen. So if there's no acidic hydrogen, they're going to go ahead and act as a nucleophile. But if there's an acidic hydrogen, they're going to act as a base. Magnesium and the halogen. We've mentioned before that the bond between the magnesium and the halogen is ionic. But the bond between the R and the magnesium, this is covalent. But for simplicity, we are showing the charge on the R like that with a negative charge. But in reality, the bond is covalent. So there is a bond between the R and the magnesium. For the alkyl lithium, the bond is ionic and it is not covalent bond. So this is the difference between both two, but both are very reactive. And both R's in there, they act as base first if there's an acidic hydrogen. If there's no acidic hydrogen, then they act as a nucleophile and attack the electrophilic site. This is an easier representation for the Grignard. This is why we work with it. And we work with the R not coupled with the magnesium, just an R with a negative charge. Halogen can be either a bromine or chlorine. So in this type of reaction here, since I have an acidic hydrogen, then the R is going to act as a base. Bases take acidic hydrogens, form a negative charge, so you're going to end up getting your conjugate base and your conjugate acid in this case. In this case, the base is not going to come and attack the electrophilic site, which is the carbon of the carbonyl, because there is the acidic hydrogen, which is more priority than the partial positive carbon. So this is why the reaction will proceed by an acid-base reaction. Now, with these types of reactions, they are water reactive. They react violently with water. So magnesium and lithium, they do react with water. So in order to make sure that the reaction proceeds to completion, you should not have water at all in your reaction. As long as the Grignard or the alkyl lithium is reacting, you cannot have water. Once they're done from the reaction, then you can go ahead and introduce the water. So similar here, over here, with this reaction, just to ensure that the Grignard is going to act as a base, you cannot have water as a solvent. So this is why we use ether. Ether is the same as diethyl ether. And diethyl ether is two ethyls that are connected to an oxygen. So this has a common name of ether or diethyl ether in there. Now the R for both the Grignard and the alkyl lithium can be any type of R in these reactions. It can be an SP, an SP2, or an SP3R. It doesn't matter. And to represent the Grignard, as we mentioned, we represent the R that has a covalent bond with the magnesium, and there's an ionic bond between the magnesium and the bromine. So the R over here, this is an sp hybridization that is connected to the magnesium. This is an sp2. And this is going to be an sp3, and this is going to be an sp2 over here. So any type of carbon that is connected to the magnesium is going to work. If I want to represent this, then take out the covalent bond and represent it as a triple bond with a lone pair and a negative charge that is connected to a carbon. So this now is going to be your nucleophile that is going to attack the partial positive carbon. So let's go ahead and have an example. Let's say, for example, if we have a carbonyl and we're reacting it with a simple Grignard. This is the CH3MgBr. The reaction is going to go as follows in here. It's two-step reaction. The first step, you use the Grignard. With the Grignard, you should use a solvent that has no hydrogen whatsoever. No water should be involved. This is why we use the diethyl ether in there. This is going to be the first step of the reaction. The second step is a simple solvent that has a hydrogen after we're done from the attack of the Grignard. So start by breaking your charges over here and introduce your R of the Grignard. Make it simple. So the R of the Grignard here is a carbon. It's a CH3. So this carbon has a lone pair and a negative charge. This is what? This is a nucleophile. Why it's a nucleophile? Because there is no acidic hydrogen whatsoever over here for this to act as a base. So this is why it acts as a nucleophile. So the nucleophile is going to come, it's going to attack the carbon and form a negative charge on the oxygen. Again, why it's attacking this carbon? Because this carbon is partial positive, this oxygen is partial negative, due to the direction of polarization from the electronegativity. So what I'm going to end up getting in this case is a simple addition. This is an addition reaction. You added the CH3 over here, and you formed a negative charge on the oxygen. Now we're done from the Grignard. The Grignard added, so I don't need this anymore. Once you're done from the Grignard, then the next step of the reaction, this is step 2 of the reaction, we're going to use a solvent. The solvent in these cases is either water or H3O+. It's any one of those solvents in there. I'm going to use the H3O+. This is the hydronium ion. And H3O+ is a product of any acid that is dissolved in water. Or I can simply use water. Both are going to be the same, but because the only role of the solvent at the end is it just to protonate that oxygen by doing an acid-base reaction. So if I use water, then this is going to be my base. And this hydrogen here is going to be my acid. So it's a very weak acid. Or I can use the base with this acidic hydrogen over here. Water is going to leave. This is the OH is going to leave in this case. Any one of those. And then my product is going to be an alcohol. The rule says that if I start with a ketone, then my product is going to be a tertiary alcohol. If I start with an aldehyde, for example, let's go ahead and start with an aldehyde. So if I start with an aldehyde and I react this with any R, so I'm going to go ahead and use phenyl magnesium bromide with diethyl ether. This is going to be my first step in there. So we agreed to break it, make it simple, and it's this carbon that is connected to the magnesium, this carbon over here. So I want to make this carbon over here lone pair with a negative charge. So this is the carbon over here that was connected to the magnesium. So I want to make it a lone pair with a positive charge. So now this is going to come, it's going to attack the carbon and form a negative charge on the oxygen. So you're going to end up having your own negative. You already have a hydrogen, but you added what? You added a benzene. This is what you added. So put it like that. Okay, it's either you put it as a benzene or you use the abbreviation, which is the pH. Whatever best for you, you can go ahead and do. Now the second step of the reaction, I'm going to go ahead and use the water to protonate the oxygen. So you're going to see over here that what I ended up getting is simply a secondary alcohol. So this is going to be my secondary alcohol in this case. If you work backwards, then what you need to do is highlight the carbon OH in there. So the carbon OH is the carbonyl. Just go backwards, because sometimes you are given the alcohol and you are asked, go ahead and find out the carbonyl and the Grignard reagent that it came from. So you highlight the carbon OH and immediately change that into a carbonyl, and then go ahead and break the bond between the carbon and your R group. Here in this case, you have two R's. It's either the side that can be the R of the Grignard or the side that can be the R of the Grignard. So if you choose this side to be the R of the Grignard, make this side the R of the aldehyde in there. Of course, you need to know that this is a secondary alcohol, and secondary alcohols, they always come from aldehydes. So tertiary alcohols, they come from ketones. Secondary alcohols, they come from aldehydes. Now, if I wish to make a primary alcohol, then in this case, I need to have hydrogens over here. I should not have any R in this case, except the R of the Grignard that I want to add. So I need to start with the simplest type of aldehyde, which is the formaldehyde. So that is the simplest type of aldehyde here, which is formaldehyde. And you go ahead and you react that with the Grignard. We can react the Grignard, as I said, with, let's say, for example, MgBr, okay, and diethyl ether, and this is step number 1. So it's this carbon over here that is connected to the magnesium. So we're going to go ahead and make this carbon a negative charge. Don't forget it's CH3. It's this carbon over here. So this is going to be our nucleophile, and that nucleophile is going to come, attack the carbon, form a negative charge on the oxygen. These hydrogens are not acidic. So this is not going to act as a base and take any of these hydrogens in there. It's just going to act as a nucleophile, attack the partial positive carbon, form a negative charge on the oxygen, and you're going to end up having your O negative in there. You have your hydrogens, and all what you did is just you added your triple bond and the CH3. So this is your R in here. You do the protonation, which is the water, and this is going to be your second step, step 2 over there. I am putting step 2. So in each one of those, you have to put step 2 there. And then the lone pairs are going to come, take the hydrogen, OH is going to leave, and you are going to end up getting your primary alcohol in this case. So this is going to be the primary alcohol. So based on the type of the alcohol that you are getting, you can easily know what type of carbonyl you started with. So primary alcohol means that I'm always going to start with formaldehyde. This means that the R over here needs to be the R of the Grignard. Secondary alcohol, it's either one of the R's is going to be the one for the Grignard, and the other R is going to be for the aldehyde and not the ketone. For ketones in there, you're producing tertiary alcohol. So choose one of the R and make it for the Grignard, and the other 2 R's, make them for the ketone. In there, they can be any of the 2 R's, a CH3 and an ethyl, or 2 CH3s in there. Any of these 2 R's can be the R's of the ketone. There's another way of getting the tertiary alcohol, and that way is to start with an ester or an acetic chloride. So let's say if we start with an ester, okay, and we are reacting this with still phenyl, magnesium, bromide, in presence of diethyl ether. This is the first step in there. So now I am starting with an ester. Ester and acidic chlorides, they have something in common, which is the leaving group. So esters always have this guy over here, which is a good leaving group in basic medium. And this is a basic medium in there because whenever I draw the Grignard, the R of the Grignard, this is a negative charge. It is a nucleophile, so the medium is not definitely acidic, it is basic, and oxygen can leave in a lone pair in a basic medium. So the reaction is going to proceed by having the nucleophile attacking the electrophile. This is partial positive. This is my nucleophile in there, forming a negative charge on the oxygen. The Grignards are very reactive, very reactive. So the Grignards are going to keep reacting as long as you form a carbonyl. So notice here what I have. I formed a negative charge and I added a phenyl group. I'm just going to write it as a pH. So I added a benzene over here. Now I'm going to go ahead and do resonance to kick out the OR. And this always happens with esters because, again, as we said, the ORs are a very good leaving group. So it's going to form a double bond. This is going to leave. And you're going to end up getting, this is a carbonyl, and it's going to be a phenyl. So see, you're back now to a ketone. So always the intermediate in the reaction of the esters before getting your final product is the ketone. Now, you cannot stop here. So as if you are back to here, over here. So this is why the Grignard is going to react again. Grignards are very reactive. They're going to keep reacting as long as you are forming a carbonyl. Once you stop forming a carbonyl, this is when you proceed to the next step of the reaction, which is the protonation. So since I formed the ketone in here, I'm going to go ahead and react this with the same Grignard again. Here you go. So I don't have to mention that the Grignard is used in excess, because the Grignard is very reactive. As we said, it's going to keep reacting as long as there is a carbonyl. In some reactions, you're going to see that this one is expressed in excess. In some reactions, you're not going to see it in excess. It really doesn't matter. It's always in excess. So this guy over here now is going to come. It's going to attack the carbonyl, form a negative charge on the oxygen. Now, the only difference here is that I don't have an additional leaving group in here. So, but I ended up adding the phenols twice in there. And these two phenols here, they belong to the R of the Grignard in this case. So now my second step, I'm done. My second step is going to be the protonation with water or H3O+. And this is going to, my arrows are in the opposite direction. The base is going to come, take the hydrogen, form the OH in this case, and I'm going to end up getting my product, which is going to be the tertiary alcohol. You know that your tertiary alcohol is coming from an ester if you have two R's that are the same on the alcohol. But it doesn't really matter because tertiary alcohols are always products of ketones, esters, and acidic chlorides. So let's say, for example, if we substitute the OR by a chlorine, so now we are doing an acidic chloride, the mechanism is going to proceed exactly the same, but the leaving group now is going to be a chlorine instead of the OR. And you're still going to get the tertiary alcohol as a product. There are extra problems in the notes and in the problem set. Practice those, please.